Okay, we'll start with the computer organization, and the first topic is von Neumann architecture. So, this was published in 1945 and it's based on the stored program concept. And according to the von Neumann architecture, both the instructions and the data is stored in the same memory. There are certain building blocks of the architecture, which consist of CPU, memory unit, I/O devices, connection structure, and register and other circuitry. So CPU basically interprets the command to be executed and generates the control signals to instruct other units to perform operations. And memory unit stores the address, instructions, and data. I/O devices input take the input of the instructions and output the results. And connection structure allows the connection between the components. And the registers and other circuitry are also part of the von Neumann architecture. So this is how the von Neumann architecture looks like. So you can see that on the left hand side we have the input device, on the right hand side we have output device. You have central processing unit. Inside of that you have control unit and arithmetic and logical unit. Then you also have the memory unit here. There are certain features of von Neumann architecture which talks about that each memory unit has multiple locations having different addresses. A computer program consists of instructions and data, and CPU processes the data stored in the memory as per program instructions. The results are stored in the memory or output devices, and registers are used by the data processing operations in the CPU. There are buses also like address bus, data bus, control bus, which are used for communicating the address, data, and control signals. So just to recap, each memory unit have multiple locations having different addresses. As we all know, computer program consists of the instructions and data. CPU processes the data stored in the memory as per program instructions. Whatever results are produced, they are stored into the memory or the output devices. And CPU also uses registers for data processing. There is a requirement of buses, which is used for communicating the address, data, and control signals. So these are some of the features of the von Neumann architecture. Apart from that, the input devices fetches data or commands and CPU executes it. When the task is complete, result is stored in the output devices. I will talk about cache. So what is cache basically? So cache is basically used to improve performance because if the CPU has to get the data from the main memory, it can be time consuming. So that's why the cache memory is used so that it can serve faster results. So cache memory basically sits between the main memory as well as the main memory and the CPU, and it's basically a small high-speed buffer memory. The data is transferred in form of words. As you know, the memory is in form of words, so the data is transferred in form of words between the cache memory and the CPU. So what's the need for the cache memory? Well, the main important use of the cache memory is performance. So ideally, the speed at which CPU requires the data is high, and the main memory, which is the RAM, is not able to match that. So to match that speed, cache is used, and cache memory is basically able to match the speed because whenever a new program comes, it is kept into the main memory. In fact, the part of it is kept into the main memory, which is being currently used. However, if there are certain instructions or certain part of the program which are not going to be used now, but it will be used in the future, and that part is going to be kept inside of the cache so that it can be immediately accessed by CPU. Now, what is cache mapping? Well, cache mapping is basically a technique by which the contents of the main memory are brought into the cache memory. So there are different cache mapping techniques. One is direct mapping, and we have fully associative mapping, and we also have the K-way set associative mapping. If I had to tell you in short, in brief, direct mapping is a cache mapping technique where the block of the main memory, a block of the main memory uh, is basically aligned to a specific line in the cache memory. Okay. However, in full associative memory, each block can actually be aligned to any of the lines, any of the memory lines that are available in the cache memory, depending on the availability. In the KV set associative mapping, as the name suggests, it's a set associative mapping. What happens is that in the cache memory, each of the lines are grouped together in form of sets, and these sets are mapped with the block from the main memory. So I will show you in a moment in terms of example. Let's start with a direct mapping. So you can think of this word mapping, and then accordingly you can write about it. So a particular block of a main memory can only be mapped to a particular line of cache, meaning a particular block of main memory can only be placed. So what is the meaning of mapped? It means that it can only be placed in a particular line of cache memory. So let me show you the example. So let's take a look. For example, let's say there are 32 words in the main memory. Each block contains 4 words. So there will be a total of 8 blocks, because 32 divided by 4, 4 words in each block. That means it's a total of 8 blocks in the main memory. As you can see, it's 0, 1, 2, 3, 4, 5, 6, 7. So there are 8 blocks. Now, let's say there are 16 words in the cache memory. This is your cache memory. So what will be the total number of lines? So total number of line, the formula for that is that total number of words divided by words per line. So 16 divided by 4. So that's 4 lines. So that's why you can see 4 lines here, right? Line 0, line 1, line 2, line 3. Now, how do I map? So there are different blocks over here. Block 0 up until 7, and here we have line 1 to 3. So how do we know which block to be mapped to which line in the cache memory? Well, for that there's a formula called I equals j mod m. Mod means modulus operator. So I is basically the line number, J is the block number, and M is the total number of blocks in each. Uh, yeah, sorry, that's the number of lines in the cache. Okay, so if you see this, this is how we calculate. So block 0, what will be the value of J? J is 0 because block is 0. Modulus 4. How many lines in the cache memory? It's 4 lines. So 0 mod 4 is 0. So that's why block 0 will be mapped to line 0. Similarly, block 2, 2 mod 4 is 2. So block 2 will be mapped to line 2. So as you can see, each block is mapped to a specific line in the cache memory. So that's the concept of the direct mapping. Now there's also something called physical address. So for physical address is divided as tag, line number, and word offset. Now what are these tags? You can see that on the left hand side you have some tags here, which is used to represent which block it is. For example, block 0, block 4. Which block are we talking about? Is it the block 0 or block 4? Because there could be multiple blocks that could be mapped to a particular line. So like as you can see, 4 is getting mapped to line, block 0 is also getting mapped to the same line. So how do we know like which block is placed inside of that? So that is determined by the tags. So tag is used to locate the block's position in the main memory. Example, if the block is mapped to the line 0, which means the words W0 to W3, which means W0 to W3 will be placed inside the line 0. But how to identify which words are being referred to? This is where the word offset comes in. So under each block there will be different words like W0 to W3 for block 0, and for block 4 it will be W0 to W sorry for block 4 it will be something else. So how do we know which word are we talking about? This is where the word offset comes into picture. So let's say that we calculate the bits size of the memory. So as we know, the main memory is actually 32 bytes. So if you can also write 32 as 2 raised to the power 5. So that means it has 5 bits. So let's say we want to access the word 9. So where is the word 9? Here is the word 9, right? Inside of the block 2. So what will become the physical address? The physical address will become the binary representation of 9. So binary representation of 9 is 01001. So out of this one second, yeah. So out of this, basically, this binary representation of 9, 1 is actually 1 bit for tag. So that goes for tag. This 00 is 2 bits for the line number. So what line number is being used? Line 0, line 1, line 2, line 3. Which one is it? Then we have 01, which is the last 2 bits. That's for word offset. Okay. Now, so tag is the block 0. So now we are inside of cache memory. That's a block 0. So 0 is determined by tag. So if tag is 0, it's a block 0. If tag is 1, it's a block 4. That's how the tag is determined. Line number. So which line number block is present? And then offset. Which word are we talking about? Is it the word 10, word 17, word 16? Which one is it? So that is determined by the offset, word offset. Okay. So that's your direct mapping. Then we have associative mapping. So in associative mapping, basically any block in the main memory, any block here can be mapped to any lines in the cache memory depending on the availability. So it is not mapped to a specific line, it can be mapped to any line. That's a difference between direct mapping and associative mapping. So this makes the associative mapping more flexible than the direct mapping. So let's talk about the physical address. So physical address for associative mapping only includes tag and word offset. So this is the binary representation of a particular block. So this has 3 bits, this has 2 bits. So we just broke the 010 into tag and 012 word offset. So unlike the direct mapping where we use the J mod M formula to calculate to find out which block refers to which line, here you don't have anything like that. Because any block can be mapped to any line. So you don't have to use any formula for calculating. Whatever the lines are available, that's where the block will be placed. Now we talk about the set associative mapping. So in this, instead of mapping only one line to one block of the memory, a few lines form a set. That's why it's called set. So two or more lines form a set, and then each block can be mapped to a particular set, which means inside that set it can be placed in any of the lines. This way, set associative removes the drawback of direct mapping because direct mapping can cause thrashing, and associative mapping, which we learned here, can cause high implement has a drawback of high implementation cost. So that is why set associative mapping has an advantage. It removes the drawback of the direct mapping and associative mapping. Set associative combines the best of the direct and associative mapping techniques. So it's the best of all. Each word in cache have two or more words in the main memory for the same index. Okay, just give me 1 second. Hi, Somaya.
Hi.
How's the preparation going on?
Um, okay, so far.
Okay. How much percentage done on the computer organization?
I was doing the section on processor and instruction set today. I think I finished around 75% of the portion.
Very good, very good, very good. You're done with all of these, no?
This is mapping,
Yeah.
direct mapping.
Yeah.
Yes, I'm done with that.
Okay. Okay. I'm just doing a recap. Okay.
Okay.
So, if one set, so now we talk about the two-way set associative mapping. If one set in cache memory contains k lines, we call it k-way set associative mapping. So one set equals k lines. So if one set contains two lines, we call it two-way set associative mapping, where k equals 2. So in this example, let's say the main memory size, which is this main memory, has 128 bytes, and the cache memory, which is this, has 32 bytes, and the block size is 4 bytes. Like each of these blocks is 4 bytes. So for the two-way set associative mapping, the total number of memory blocks will be main memory size, which is 128 bytes, divided by each block size, which is 4. So total become 32 bytes. So 32 blocks. So B0 up until B31 makes a total of 32 blocks. Then total number of lines equals total cache memory size, total number of words divided by each block size, which is words per line. So 32 divided by 4 is 8 lines. So 8 lines in the uh, cache memory. L0 to L7. Talking about the physical address is divided into three parts: tag, set, and word offset. And how do we know how many bits will be for the physical address? Well, we just have to raise 128 can be written as 2 to the power 7. So this 7 becomes the 7 bits. And the tag, we divide the 7 bits into three parts. We give 3 bits to the tag, 2 bits to the set number, and 2 bits to the offset. Now, uh, how do we know the sets, number of sets? So number of sets equals number of lines. So there are 8 lines divided by number of lines in each set. So this is a two-way set associative mapping. That's why there will be two lines in each set. So that's why we divide by 2. So there will be 4 sets in total: 0, 1, 2, 3. Now, how do we map the block to the set? We use this formula: I equals j mod v. I is the number of set number, basically. In the previous example, when you're using direct mapping, I was the line number, but here we have set number as I. J is the block number, like 0, 1, 2, and V is basically your total number of sets in the cache memory. So in the previous example, in direct mapping, this was the line total number of lines, but because this is set associative mapping, this will be the total number of sets. So 0, which is block number, 4 is the total number of sets. So block 0 will be mapped to set 0. Advantage of set associative mapping is that, unlike associative mapping, we do not need to search the entire cache memory. So entire cache memory does not need to be searched. Only that particular set, all the lines in that set needs to be searched. Registers. So may you done with registers?
Yes.
Okay. Let's do a recap. Can you read out?
Registers are fast memory which are used to accept, store, and transfer data and instructions that are being used immediately by the CPU.
Yeah.
Registers are faster than the cache memory and the main memory.
Right.
They can be considered as a group of flip-flops. Each flip-flop is capable of storing one bit of information. They are also called processor registers. They may hold an instruction, storage, address, or any data, a bit sequence, or individual character.
Okay.
The common registers are accumulator register of 16 bits. It holds temporary data for short-term intermediate storage of arithmetic and logical data in CPU. The memory register or MAR, this should be memory address register, right?
Where?
MAR is short for memory address register.
Okay. Let's update that.
It has 12 bits. It holds the address for the memory. The stored memory address will either uh,
Hey,
it
such
stores
such
the memory address from which the data will be fetched to CPU. So the CPU will get the data from the memory
hey,
address,
such
or
memory
address from which the data will be fetched to CPU. So the CPU will get the data from the memory
hey,
address, or
memory address. Sorry, 1 second.
from which the data will be fetched to CPU. The CPU will get the data from the memory
Hey,
address, or
memory address. Sorry, 1 second.
from which the data will be fetched.
Okay, cool. Can you hear me, Sumaya?
Yes,
Okay, cool.
I think there's
That's
a delay.
delay was there because I was actually playing the. It was not muted. The YouTube live was not muted. That's why.
Oh, okay.
Yeah. So again, I have to change this to MAR, right? Memory address register.
Yeah.
Okay, carry on.
The program counter, again, the memory address register, it's used for reading from memory. The data addressed by MAR is fed into MDR.
Mhm.
And when writing, the CPU writes data from MDR to MAR. The program counter is of 12 bits. It holds address of instruction. It holds address of the next instruction.
Okay.
It holds the memory address or location of the instructions being executed by the CPU at the current time of the next instruction that's going to be executed.
Okay. Program counter.
It holds address of the instruction. Once the CPU finishes the current execution, the program counter increases by 1. Faster execution of instruction.
Mhm.
What does that mean?
Which means that instructions are executed faster because of this calculation. It's able to track it and calculate it.
Okay.
Yeah.
Helps in tracking the execution points of instructions. The
Hmm.
input register has 8 bits. It carries input characters. It takes the data from the input devices like keyboard or mouse and carries input characters.
Yep.
Instruction register has 16 bits. It holds the instruction code. It is part of the CPU's control unit. It holds the instructions currently being executed or decoded.
Right. Sumaya, I was thinking that would you be able to help solve some of the problems also? So I'll tell you what I mean. 1 second.
I can try. I haven't practiced a lot.
I'll tell you which one are those, and let me know if you practice those.
Okay.
Okay. Uh, do, 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 do. Have you done ones and twos complement?
Yes.
It's very very important from exam points of view. So I'm going to paste that here. Hold on. And then maybe you can solve it using the. We are not using Zoom, so you can't do anything, right?
Yeah.
Then how do we solve it? The question. Maybe if I give you access to this slide, you can solve it here by opening that slide. And because I'm sharing the same slide, whatever changes you make will be shown. What do you think?
Yes, we can try that.
Or you can also share your own screen. Like, do you have anything that you can, uh, like from your end, you have any online tool where you can draw and write or something?
Mm, I can do it in Docs or look for an online whiteboard.
Okay. Can you try sharing your screen? I'll stop my share.
Okay, one second. Okay, you can see my screen.
Yeah. Not okay. Let me add that to the stream. Now you can see. Uh, can you share that Google Doc so I can paste the problem sum over there, question over there? Please share the link of that in the private chat. No, 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 no. Editor. It will not allow me to paste. Click on share again. Change viewer. Change viewer to editor on the right hand side. Yeah,
Okay.
yeah. Now copy the link. Private chat. Yeah. So that's these are the questions.
Okay, so ones complement is simple. You switch the ones to zeros and the zeros to ones.
Okay.
So for this one, it will be 0, 1, 0, 1, 1, 1, 0, 1.
Is there any calculation or any explanation needs to be done, like, or directly we can write?
You can write it directly.
Okay. So that's clear.
So
What about the big one? Go ahead.
when you add the number with its ones complement, then the sum will be 1, 1, 1, 1, 1, all ones.
Mm-hmm.
Then with the two complements, you add 1 to the ones complement. So an easy way to do this is you write the starting from the least significant bit.
Mm-hmm.
You write the same digits up to the first one. So 0 and 1 will stay the same,
Mm-hmm.
and then the rest of the bits are all complemented. So
Complement.
yes, 1,
Okay.
1, 1, 0, 1, 0.
Okay. So you're saying that the the last two numbers, which is 1 and 0, the last two number from the right,
Yes, these
they
are the
remain
same
okay, and rest
up
of
to
them.
the up to the one, the least significant one.
Oh, up to 1 is this, like the moment you find the closest one until
Yes,
that number. So
yes,
if the last three numbers were 100, then we'll go to 1 up until 100, right? Those three numbers we will exclude, and we'll make complement of all others. Correct?
yes,
Okay.
yes.
So, so what will happen for the second example?
The second one, the ones complement is 1 1. How many are there? I think 8.
And
And
because here we don't have one,
the two's complement will be the same. So I think I need to recheck this,
okay.
but I think it's going to be the same as the number 000.
In the first example, okay, the
Yeah.
two's complement is the two's complement is the complement of one's complement, or is the complement of whatever the number was given?
No, it's the ones complement plus 1. So you
Okay,
can see that at the end it's 0 1 and it changes to 1 0. You add 1 to it.
correct, correct. Okay, got it.
And if you add 1 to this ones complement,
Hmm.
then there will be an extra bit
So we don't want that. That will not be two's two's complement is basically uh, from left hand side, go up until the closest one, and don't change anything on up until then, and anything before that you
from
changed it one complement.
from right hand side.
Yeah, correct. From right hand side. That's right. Okay. Let's do the last one. That becomes 0 0 1 1.
Yes, 0 0 1 1 0 0 1 1.
Hmm.
Then for two's complement, it will be 1. Let me start from here. So the 1 will stay the same, and then the all the digits before it will be reversed. So
Okay.
0 1 1. Oh wait, sorry, I was looking at the ones complement. Sorry, that was wrong. It's 0 0 1. That's the least significant one from the right hand side, and then the rest of them are reversed. 0 1 1 0 0.
Okay, good. Okay, that's clear. Let me see if next problem, if you have done it. So next problem is, let me paste that and let me know if you've done it. Okay.
Okay.
Okay. Which one? It's important according to exam.
Yes, I've tried a few problems in this.
Can you try one of this?
Okay, so I have to convert them to binary first. 50 is um,
Convert
32 plus 16
to binary.
is 48. 32 plus 16 plus 2.
110010.
We need 8 bits, so 1, 2, 3, 4, 5, 6.
You want the 8 bits, so you'll put 00, na? Before that.
Yes.
Okay. 10010.
Uh, then 5 is 0, 0, 0, 0, 1, 0, 1. Yes. So we take the 2's complement of 5, which
Hmm.
is 1. Okay, I think that is correct.
So
So
what's
all of the
happening here?
numbers are reversed except for the last one.
Sorry, I'm not getting it. What happened here? So we converted this into a binary, right?
Yes, and
We
then
made
took
it
the
to
2's
binary.
complement of 5 because that is negative. So for minus 5, we'll take the 2's complement like this.
But it's anyways telling us two's complement here. So what is like what's the difference in negative and positive?
For the negative numbers, we take the 2's complement.
And for positive numbers?
We take them as it is. They have a sign bit, so the first bit should be 0. When
Hmm.
we take the 2's complement, the first bit will become 1.
Okay.
The sign bit will be 1. So
So I'm
here,
going to write that
for the
here. Okay.
2's complement, the last one will be the same, and everything else is reversed.
Okay. Let me just write that down. So you said that for positive numbers, first is not changed, or the whole thing remains as it is.
Yes.
The two's complement is same as whatever that number is for a positive number.
Sorry.
See now what I've written here. For positive numbers, two complement
Yes.
the same number in binary. No change. For negative numbers, can I put negative here or no?
No,
Okay, I'll put.
that's
I'll
the
first.
positive 5.
Okay, for negative number, first get the binary conversion for its positive number, then add 1 at the start to convert it to negative.
The 1 will automatically come when you change it to the 2's complement, the one
So,
representing the sign bit.
so my question is that this was a positive number. So how did we convert it to a negative number?
By taking the 2's complement.
Okay.
So actually, the 7 bits, those are the actual number, the magnitude, and this bit is the sign bit.
First bit, example 0 is the sign bit, and the rest of the 7 numbers are what?
Uh, those are the, it's for the number.
That's fine. Then take the two's complement by changing all numbers or by um, complementing reversing 1 and 1 to 0. Then take 2's complement by complementing by complement reversing 0 to 1 and 1 to 0 for all numbers except until you find 1 from the right. We can make that bold. So we can this number. We excluded this number and for rest other numbers we change it, right?
Yes.
Okay, good. Cool. So similarly we'll do it for these guys also. There's no difference, right? So like
Yes.
in this example, what's going to happen is that it will stay the same. We were not going to take out two's complement because they both are positive, correct?
Yes.
Okay. Okay, let's move on. Let me see another question. Mm,
I
do you
didn't
know
add the numbers. Should I do that too?
which one?
I didn't add the numbers, only converted them to binary.
Oh, okay. Yeah, let's add it. Let me put a question mark here. So, yeah, you carry on. I'll
Okay.
put bold.
Maybe I should put a table here for that.
You can if you want to. It's a very confusing as well, these questions. So damn confusing. People have not explained properly.
Um, I think it was explained quite well in the book.
Really? Okay. We have
Yeah.
to get it.
So here I'll put the number in this column. Um, Here carry 50, -5. I should have one more row. Okay. And result here.
Okay.
50 or 0, 0. -5 is this is the sign. So 0 plus 1 is 1, 1 plus 1 is 0, 1, 1, 1, 0, 1, this is 1 1 and 0 1. Okay, so 0 here, and there is an extra carry. I should have made another column.
Let me see if we can add that. Mm, what's this? Column you want to make, right?
Yeah,
Uh,
it's here.
not allowing to make another column.
So the carry that comes in here in the sign bit column is carry into sign bit,
Mhm.
and we also have a carry out of sign bit, which I should have put another column for. So
Eh,
if there is both carry into sign bit and carry out of sign bit, the result is valid. There is no overflow. If there is only one of them, then there is overflow and the result is wrong.
okay, let me understand from here first. Okay, so you put two numbers there. Oh, you we moved it up and down. Sorry.
Or did you change? Or,
No, it's fine. So 0 plus 1, sum is 1, carry is 0. Can I put 0 here? Or
yes,
don't, not required? Not required, I
I
think, right?
think it doesn't matter.
1 plus, yeah, 1 plus 1 is, the sum is 0, carry is 1. 1 plus 0, sum is 1, carry is 0. 1 plus 0, sum is 1, carry is 0. So same formula here also. 1 plus 1, sum is 0, carry is 1. Same thing goes here. Same thing goes here. So basically you've added them, right? What is that extra thing that you're talking about? I'm getting confused with that.
When you add 1 plus 1, there is 0
Yeah,
1. I have to also put an extra column to show that,
the
to show
carry,
the
right?
extra carry. Yes.
But wouldn't that sit here like that?
No.
So where will that go? Will just stay
It
there
is
like that,
called
something like
carry
that.
out of sign bit. Okay, you can
Okay.
put it there. So usually there is another column that shows that.
The last one, carry, is signed out. What do you call it?
Carry out of sign bit, because it's coming out of the sign bit. What the carry under the sign bit is called carry into sign bit.
If there wasn't anything that was overflowing, then what will it be called? So this was carry out, which is clear. But in case, let's say there was nothing carried out,
Then if there was a carry into sign bit but nothing carried out, then there is overflow and the result is not valid. And if there
if
is
there
a
is,
carry,
if there is no last carry, जैसे यहाँ पे ये extra carry नहीं है, then
then there is overflow.
and the result is what?
The result is not valid, it's wrong.
It has to have a carry. Okay. But did the question ask that? No, right? Only if it asks, we have to say that. If it doesn't ask, we don't have to say. Correct?
No, we do have to say it because then the result is not valid if there is overflow.
Okay. So in our
It
case,
won't
there
be
is no
correct.
overflow. Correct?
Yes. There is a table that I put in my notes. So to
Can you
figure out
paste
if
it
there
there?
is overflow, it's like doing an XOR of the carry in and the carry out. Okay, I
Can you paste
pasted.
that table here? Can I see it?
Yes,
Maybe paste it here only in this Google Doc.
yes, one second. It's not coming. Okay, this is the conditions of two's complement notation while addition.
Carry in to sign bit, no. Carry out to sign bit, no. Result is fine. Okay. Can you give me an example of carry in to sign bit? So we in our case it was carry out. What is carry in?
We have a carry into right here. It's what gets carried in the sign bit column.
Okay, so we do have the carry in here. Okay, but
Yes,
in
our
our
condition is this one. Yes
this
and
one
yes.
carry out. So in a, which one out of these is our condition?
The second one, yes and yes. Carry into the sign bit and carry out of the sign bit.
Okay, so if there was no carry here, let's say here and here, then it will be no no. Correct?
Yes. Then
Okay,
also the result is correct.
okay,
In other
but
cases, it is overflow.
right. In case if there's a carry out but no carry in like that, then it's incorrect. Overflow. Correct?
Yes.
Got it. Cool. Let me see another question.
Do you want to convert this result back and see if it's correct?
Yeah, let's do that. So result is 100101101, right?
101101.
Result is starting from 1, right? Or not?
Yes, yes.
Okay.
It's,
Correct?
uh, you put an extra 100 here. It was just 00. We
How?
don't add. We don't put the extra bit. Only the 8
Okay.
bits are counted.
Okay. Yeah, it's very confusing if you ask me. Not easy.
It's correct. The result is 45.
Good. So result is 45, which is 50 minus 5 you check. Correct?
Yes.
So in exam you're going to be sure short that whatever you have written is correct. Right.
Yes.
So you converted 45 into binary, right? Checking the result.
Yes. Or you can convert this back to decimal.
50 minus 5 equals 45 to binary So when you converted, what did you convert back? You converted 45, right?
No, I
Into
converted
binary.
the binary into decimal.
Where
Yeah.
did you do that?
I just did it in my mind.
Oh, okay.
You can just add the powers of 2 and do it.
Hmm.
I don't think it's required to write, but just to check.
Okay. Okay. Let's move on to paste another question.
And one more thing, if the result is negative, means you have a 1 at the start, you have to
Hmm.
take the 2's complement again.
Wait 1 second. Okay, let me paste another question.
Okay.
Mm, can you have you done this? Write a BCD equivalent of three numbers.
Yes, I did it. I don't remember it
Okay.
very well. Let me check my notes.
Can you check your notes and tell me?
Yeah. So in BCD, each decimal digit is represented by 4 binary digits.
What is BCD?
Binary, uh, binary coded decimal.
Okay. Okay.
Okay, I'll put a table for 23. Should also put the sign digit.
Now think about how many columns you need. Take extra
Yeah.
column, it's fine, but don't.
Okay, I think this. So one column for the sign digit and one for each decimal digit. So 3 in binary is 0011. 2 is 0010. And in BCD, the sign digits are represented by 1100 for positive and 1101 for negative.
Sorry, I didn't understand. Can you explain that once again?
For positive sign, it's represented by 1100. For negative sign, it's represented by 1101.
Okay, like the sign bit you're talking about.
Yes, the sign bit,
Let me write that down.
sign
So for
digit.
positive number, the sign bit is represented by. 1100.
Yes, and
One
for negative
like
it's 1101.
11. Sorry, what is that?
1101.
Okay. So because in our case, as in our case, 23 is positive. That's why signed digit is 1100. Correct.
Yes.
Okay.
Step for the decimal also it is the same way. Convert each digit into 4 bits of binary.
How is this one calculated? This two. What's this 2 and 3 here?
This is the binary.
Binary. Okay. For two and
3 in
three.
binary is 1 1. So you just put extra zeros to make it 4 bits.
Oh, okay. Okay. Got it. Is that the answer? Is that all it is?
Yes.
For 23, we break into 2 and 3 and find out their binary. Example 0010 and 0011. Correct? So
Yes.
just we have to create this chart. I'm going to put this as a
Yes.
negative number. What will you do with a decimal?
The
Will
decimal
you
is the
multiply
same
it
way. You
first?
just put the dot of the decimal.
Can you do the second one? So I'll put like this is the first one. A, B, C. A. There only you are putting. Put it down now. Answer B. These are three different questions, right?
Yeah, I accidentally put it there.
Okay.
Sit right there. It's 49.25. So here also you just convert the digits into binary.
Uh,
5 is 0100.
mm,
2 is 0010.
mm.
And
For
it's in the
decimal, you
decimal.
just put decimal there.
Yes. 9 is 1001. And 4 is 0. Wait, I think I put 5 wrong. 010 is 0100. Oh, and the sign digit is 1101.
correct? Find out there. So 0, 1, 0, 0, 1, 0, 0, 1, decimal 0, 0, 1, 0, 0, 1. Correct?
Yes.
Okay. Okay. Cool. So similarly, we'll do it for that also. तो मैं एक break लेते हैं क्या या you are busy now after this?
Mm,
कुछ
I'm
और
not really
questions?
busy. I'll go back to studying.
Okay, कुछ questions और हैं जो solve करने हैं, which I am not getting the answer for. Uh, I think there are just one or two. So, and they're important. I've seen in the exam
Okay, I
paper.
can try.
So, so can we join in like uh, 20 minutes? Will you be available?
Yes.
Okay, I'll keep this live session on. So either you can stay in or you can join back in 20 minutes, like at 8:50. I'll not end the broadcast. Okay.
Okay.
Okay. Thanks. Hi, Sumaya, I'm back. Can you hear me? Hello, Sumaya, can you hear me? Okay, so now we're going to talk about the instruction cycle. Um, Instruction cycle is basically a cycle that is used by the CPU to perform the instructions and from the lifespan of the time of boot up until it's switched off, shut down. Okay, so it's a cycle used by followed by CPU to process instructions. The different phases in the cycle of instruction. First is the fetch, second is decode, third is read, and fourth is execute. So fetch means fetching the instructions from the memory. Instruction fetch will bring the instructions placed in the memory location into instruction register. Decode the instruction will decode the instruction. So encoded instructions present in the instruction register is interpreted by the decoder. Read will read the effective address from the memory. Once the address of the operand are known, they are brought into the CPU register to perform operation. Execute will execute the instruction and results are temporarily stored in the location. So fetch fetches the instructions, decode interpreted encoded instructions are interpreted by the decoder, read. So once the address of the operator are known, they are brought into the CPU register to perform operation, and execute executes the instructions. So this is the instruction cycle, which is fetch, decode, read, and execute. Now we talk about interrupt. Interrupt means stop the ongoing activity. Uh, in computer system, an interrupt stops the execution of the next instruction in an instruction cycle. An interrupt can occur due to several reasons. For example, program instruction itself causes an interrupt, division by zero occurs, a result exceeds the limit, etc. Clock initiated programs time limit expired, IO requests wait, hardware generated memory errors. So interrupt stops the execution of the next instruction in instruction cycle. It can occur due to the program itself. For example, if the division by zero occurs, the result exceeds the limit. Clock initiated, the program's time limit expires, input output request wait, hardware generated memory errors. CPU is executing a program, say X, and its decode stage of its ith instruction. Hello, Sumaya, can you hear me?
Yeah.
Okay, remove that. Can you share that sheet
Yes.
that you were sharing?
Okay.
I'm going to paste the question. Tell me if you've done it.
Okay.
Check.
No, I didn't do this.
Have you done it?
No.
Okay. तो देख लेना एक बार, ये इम्पोर्टेंट है. एक और है.
I think this is in the assembly language programming.
यस. असेंबली पे एक क्वेश्चन तो आएगा ही, दोनों में से एक. लास्ट वाला इज लाइक वेरी वेरी इंपॉर्टेंट.
Okay.
ये लेकिन किया नहीं है ना ये.
No.
ओके. एक मिनट. Last question and then we can call it a day. I'll paste it there.
Okay.
Yeah.
Yes, I did this.
Can you solve it? And also explain how you're solving it. This is first question, no? This is B, C. बहुत बड़ा है यार ये कंप्यूटर ऑर्गेनाइजेशन. सरदर्द एकदम.
Okay, so binary numbers to decimal and make the table
Yeah.
for 48 columns.
No, not there, not like that. Can you put it down? Let the questions be on top. Let's not mix it up.
Okay.
Yeah.
So first I'll write the binary place values here.
Okay. Are you typing anything? Because I can't see anything.
I'm typing now. Can you see the table?
No. Oh, it's down at the bottom. Sorry. Yeah. Fine.
So first is 2 raised to 0. I'll just write 1. And then okay, 2. Oh, actually it has a decimal point, so can't do it like
Yes.
this. Okay, I'll write the binary number first. It's 1100
So Maya, where are you based? Which place?
in Pune. I stay in market here.
Pune. Okay. What center have you selected?
Azam campus. Abedine.
I'm also coming there. We'll meet
Okay.
together. My sister is also coming.
She's also doing the same course.
Exact same thing. Yes.
Okay, so for the what is this part called? The one before the
So we have to
decimal.
convert binary to decimal. Yes.
The part before the decimal point, we'll start by putting the place values, powers of 2,
Hmm.
1, 2, 4, and 8.
Don't you think you needed another row? Can I add that another row?
Yes, I could have put a column also to label the rows, but I think it's okay now.
It's fine. I think. That's good. You want another column? Column or you want the?
A column
So
to
can you?
label the rows, like the first one would be binary place values, then binary, then
Okay. Don't know if we can do that now.
I think it's understood.
Okay.
Then for after the decimal points, you have a 1/2.
What is it? Half.
That's the place value. Like in decimal, we have 1/10, 1/100. In binary,
Mhm.
there is 1/2, 1/4, 1/8.
Okay.
Then you multiply each binary digit by the place value
Yes.
and write it here. So 8,
Becomes 8.
4, and these will be 0.
Oh, this will be 0 because 0 multiplied by
Yes,
1 is 0.
yes, that is 0.
What will this be?
This is point 0.5.
Are we actually going to write zero point 0.5 there?
Yes, because we need to add up everything after.
Okay.
Then 0.25. This is 0, and this is 16.
What are you multiplying? 0.625. 0.0625. Hold on.
Can you delete mine? Okay. And then you add up all of this. So this part before the decimal will become 12 point um, 0.75 plus 0.0625.
What are you adding?
The
8 plus
numbers
0.
after the we add the numbers before the decimal point and the numbers after. So 0.5 plus 0.25 plus 0.0625, 0.8125.
You want me to calculate this?
I calculated it, it's 0.8125.
Okay, correct.
Yes. I think we should check the answer to make sure.
How do we check the answer?
I'm just googling it.
Okay.
101. Yes, it's correct.
Okay. Next question. The first one is 2 to the power 0, na?
Yes.
Then 2 to the power 1, then 2 to the power 2, 2 to the power 3. So let's do next one.
Okay.
The value is 101. I think we can convert it. It's not a big deal. We can skip the part B because it's the same way, correct? We don't have
Yes.
to actually do that. Let's do the C one,
Okay. What was
23.
that? Decimal to binary and then to hexadecimal.
Yeah.
Okay.
Okay. Let's ensure we create extra columns this time so it's understood what each of these are. Like if we come back and see them later on, we should know. Just check if we added extra columns.
I added some extra. So here, one second, I'm checking my notes.
Okay. Is this the same notes you put? You've shared the link, Google Drive.
No, I have done these in my notebook.
Okay.
Okay, we put the place values here as well.
Okay.
Mhm. I can go up to 16 as 32 is bigger than 23. So these are binary place values. Then you write the number in powers of 2.
Yeah.
So 23 is 16 plus 4 plus 2 plus 1. So
Okay. So
in
you
all of those powers, we put a 1. And there is no 8,
like
so
that, like I have
that will have
written.
a 0.
Is this
Yes,
correct?
yes. Maybe you can also add the. No, I think that's correct. The 2 raised to 3, that's 0, so I need to put that. Then to convert to hexadecimal, we have to group these uh, bits into groups of 4.
Sorry, I didn't get this part basically. Is this conversion into binary?
Binary. Yes.
Okay. So what is this power you're talking about here? Breaking into what does that mean?
That's to figure out which place values will have a 1.
Okay. Are we not
So
going to start it
this
from
number
behind?
can be written as 1 times 16 plus 0 times 8 plus 1 times 4 plus 1 times 2 plus 1 times 1.
Okay.
So there's 116, 0, 8, 1, 4, 1, 2, and 1, 1.
Okay. So this is binary number.
Yes. And then for converting this to hexadecimal, we group the binary into groups of 4. It looks like I'll have to move these
Okay.
column labels. Can we remove some columns here?
No, I don't think so.
Okay, I'll try to write it like this.
Okay.
So the first group will be 1, 1, 1, 0, and the next one will be 0, 0, 0, 1. So I added extra zeros at the start so that I could make groups of 4
Okay. How did these values came? Like all these.
from the binary, from the binary number at the top. I just put extra zeros at the start.
What happened to this number? Where did this go?
Which one?
It looks like you've just copied from the top. These are just the replica of.
Yes,
But
that
what
one went
happened?
here. I put a space to show the space between the groups.
Oh, okay. You've grouped them together.
Normally you
Got it.
would write it right under, but I can't write it like that here.
Understand. Understand. So you've grouped into 4 and 2. Correct.
Into 4 bits.
4 bits. So
Yes,
this 4 bits.
two groups of 4.
Oh, okay. So they looking separate because of the width of this group. Now it's looking proper. So
Yeah.
these are together basically. These are together.
Okay, I'll add another row, and here I'll put the hexadecimal place value.
In exam, how will we know what those values are hexadecimal value? Are they going to give us some chart? Or we have to remember it?
No, you have to remember it. So the hexadecimal place values, they go 8421 for each group.
Hmm.
So 8, 4, 2. Then just like we did with decimal, you multiply the digit by the hexadecimal place value. So this group, it's going to be 1 plus 2 plus 4.
Hmm.
You are multiplying 1 times 1 plus 1 times 2 plus 1 times 4 plus 0 times 8. So it's 7.
Sorry, I didn't get where this come from. Is this coming from some chart? Is hex values?
No, they're just 8421. For each group of 4, you put the place values 8421.
Oh, okay, got it.
If you're doing octal, you put 421 and make groups of 3.
Okay.
So when you add up these 4 digits, when you multiply by the place value and add them up, you get 7.
How are you multiplying? Can you explain one of them?
0 times 8 plus 1 times 4 plus 1 times 2 plus 1 times 1. The
Zero times.
binary digit is being multiplied by the hexadecimal place value.
Okay, so uh, binary digits is being multiplied. Can you place your cursor over and show me which are the ones you are multiplying?
Here 1 times 1 plus 2 times 1 plus 1 times 4,
Um,
and this is 0. 0 times 8.
One second. Can you repeat that again?
1 times 1 plus 1 times 4, 1 times 2 plus 1 times 4 plus 0 times 8.
Okay, got it. Got it. Got it.
Then for the next group also you do the same thing. There is only uh, one bit
Yeah,
that's
answer will be
not.
one for that.
Yes,
Yes.
and it's 17 hexadecimal.
Answer is 17, correct?
Yes. So if you get a number 10 or 10 to 15, you have to put the letters A, B, C, D, E, F,
Okay.
the
But they
equivalent
will give
letters.
that in the exam, right? Or we have to remember it.
I think you remember it.
Okay. Okay. Perfect. So I think that's all. That's about it. I think we can skip the others. They are also very similar to what we have solved. We've solved at least one example of that. That's good. Cool. Thank you so much, Sumaya. Do you have any questions?
No,
Okay, good. Cool. So let's meet tomorrow then. And all the best for your studies. And thank you so much for helping us out.
you too.
Bye bye.